Hello guys, in the last class we discussed exact equivalent circuit when referred to the primary. So here what we have done, we have transferred all the components present in the secondary side to the primary, that is E2 become E2 dash, R2 become R2 dash, X2 become X2 dash and ZL becomes ZL dash. Okay, so now what we are going to do is we are going to transfer all the components present in the primary into the secondary. Okay, so that will become what? Equivalent equivalent circuit when referred to secondary. Okay, so once again I tell you, I will be going to transfer these all components into the secondary. So R1 becomes R1 dash, X1 becomes X1 dash, R0 become R0 dash, as well as X0 become X0 dash, as well as E1 becomes E1 dash. Okay, we shall see that. Okay, you can see all things have transferred here. R1 become R1 dash, X1 dash, Z1 dash. Yes, this remains same. Yes or not? The secondary side components remain same. I2 itself, I2, R2, X2, V2 is V2 itself, ZL, and again E2 will become E2. And R0 has, like I said, R0 has become R0 dash, X0 has become X0 dash, as well as I0 has become I0 dash. Because I have transferred all the components from primary to secondary. Again, yes, V1 has also become V1 dash. Okay, so here what happens, the formula with respect to this is a little bit changed when compared to this. Here what happened when I'm going to transfer secondary to primary in this circuit, what happened there? It was divided by k square. Yes or not? R2 dash is equal to R2 by k square and I2 dash is equal to k times of I2. Now it is reverse. Whatever it is there except this, everything is reverse. If it is divided means now it becomes what? Multiply by k square. If it is divided by k means it will be multiplied by k. If it is multiplied by k means it will be divided by k. If you remember one, others will be same. You can see here R1 dash is equal to k square times of R1, and like I said it is multiplied, and if R1 dash is, if you remember on this formula, then X1 dash Z1 dash will be also same. Then E1 dash is equal to what? K times of E1. Here it was what? K, E2 by k, but now it is what? K times of E1. Again I1 dash is equal to what? K times of I2. Here in the earlier formula, that is when referred to the primary, I2 dash is equal to what? K times of I2, but here it is what? I1 dash is equal to I1 by k. Anyhow we have transferred primary to secondary, right? So I1 dash will become what? I1 by k, and similarly I0 dash will also become I0 by k. Okay, so this is what we have formula with respect to the equivalent circuit when referred to the secondary side. Okay, so let us reduce this again to simpler circuit. Okay, so that's why it is called as what? Approximate equivalent circuit. Okay, it is not 100% true. It has got its own flaws. So that's why it is called as approximate equivalent circuit. Now what I'm going to do here is, and I'm going to here shift this exciting circuit towards extreme left. I'm going to shift this exciting circuit towards extreme left of the circuit. So what happens if I shift it? The diagram would look somewhat like this. Okay, R1 X1, R2 dash X2 dash. This is again referred to primary. Okay, approximate equivalent circuit referred to primary. Here you can consider this. Okay, this is when referred to the primary. Here I'm going to what? Shift this whole exciting circuit towards the extreme left. So X1, R1, everything remains same. Just it is shifting. By shifting and all, we are little bit of disrespecting mathematics. So that's why it is called as what? Approximate. Okay, because the value will change. So that's why it's called as approximate. Here you can see I1, I0, IC, IM, R0, X0, everything is same, just shifting it is from primary. Again secondary components will be what? R2 dash, X2 dash, V2 dash, ZL dash. That is all same because it is referred to primary, right? This exciting circuit was here in between here. Yes or not? Now I'm going to shift this exciting circuit from this point to this point, extreme left. Okay, so this is referred to primary. Now if I want to add R1 plus R2 dash, you know that it is called as R1E because already we have proved that. Again X1 plus X2 dash will become what? X1E, and together I can call it as what? Z1E, and this remains same. I0 IC IM, R0 X0, V1 is V1 itself, V2 dash is equal to V2 by K, this you already learned, and load ZL dash will remain as it is. Okay, so this is approximate, not 100%, but to make the things much simpler, you can consider this diagram, approximate equivalent circuit when referred to primary. Okay. Now coming to the voltage regulation of transformer. Okay, so this topic is to know what exactly the voltage regulation of transformer is. Why is it necessary? Okay, so what is voltage regulation? In simple words, if I say, it is what? The difference of net voltage present in the secondary to the ratio of terminal voltage V2, where E2 is what? E2 is the secondary terminal voltage on no load, whereas V2 is the what? Secondary terminal voltage on given load. So here what happens, when I keep my transformer open in the secondary side, then what happens? E2 will appear. Okay, then what I get? E2 will appear because I have not connected any load. Again, E2 will be more because E2 has to supply V2, right? Because it has to supply the losses I2 R2 as well as I2 X2. Yes or not? So if I keep my transformer open in the secondary side, it is nothing but what? I am going to get what? Induced EMF, that is in the secondary side E2, secondary terminal voltage on no load. Whereas V2 is what? V2 is that voltage I am going to get at the terminal ends of the secondary side after connection of the load. Okay, so secondary terminal voltage on given load. Okay, so here we know that E2 and V2 will be not same because E2 has to supply V2 as well as I2 R2 plus I2 X2. So that's why it is the difference of that voltage divided by terminal voltage V2. Okay, again anyhow both are in terms of volt, and again both SI units gets cancelled, so voltage regulation is represented in the form of PU, per unit regulation, means it has got no any dimension. Okay, it has got no any dimension. So one more thing we need to remember here is, your terminal voltage V2 does not depend on just only the magnitude of the load, but also it depends on the power factor of the load. Okay, so first V2 depends on the magnitude of the load as well as it also depends on the power factor of the load. Power factor in sense, on sometimes you will be connecting resistive load, sometimes you will be connecting inductive load, sometimes you will be connecting capacitive load. So V2 depends on both of the things, magnitude as well as power factor. So just simple words, remember voltage regulation is equal to E2 minus V2 by V2 into 100 in terms of percentage. Okay, so again so now question arises, voltage regulation can be positive or it can be negative or it can be zero. Okay, so the such questions will arise. So your voltage regulation can be positive as well as negative as well as zero. So first let us see when it can be positive. Let us say you have connected an inductive load. Okay, say you have connected an inductive load. So what happens when you connect inductive load? So what happens? V2 will drop. V2 will drop lesser than E2. In that condition, what happens? Where E2 is greater than V2 for inductive load. So what happens? The difference will be positive and the voltage regulation will be positive. Okay, for inductive load. Again, coming for the capacitive load, there is a condition where V2 is greater than E2, or you can call E2 is smaller than V2. In that case, what happens? If V2 is greater and E2 is smaller, obviously the difference will come in the negative. So if you take the regulation, means the voltage regulation will be what? Negative for capacitive load. And coming to the zero regulation is possible only when you connect pure resistive load. Only when you connect pure resistive load, the voltage regulation can be zero. That is, E2 will be equal to V2. So what happens? Difference will be zero. So voltage regulation will be also zero. Okay, that is your voltage regulation when it is zero. And it's again for the ideal case, your voltage regulation will be never zero, no matter how pure your electrical load is concerned. With respect to secondary, always it has some percent of regulation always exists for practical transformer. Only for idealistic we are saying voltage regulation is zero. Okay, so you may get question in the competitive exam as well. So what is the best voltage regulation for a practical transformer or for any ideal transformer, which is the best? Like they'll be giving a 0, 50, 60, 80, 100 like this. You will be getting option. By mistake also you have to not put the answer like 70, 80 or 100%. So best regulation one transformer can have is 0%. Okay, so 0% is the answer, best regulation. Okay, for ideal regulation value of your transformer is 0% and not 100%. Okay, so in that case there are the three cases where your voltage regulation will vary from inductive to resistive, inductive, capacitive as well as resistive. Okay, and you can see over here ideal voltage, at the dotted line you can see ideal voltage. What happens? I told you V2 is equal to E2. In that case voltage regulation will be 0. Okay, voltage regulation will be 0. But for leading power factor what happens? If I use capacitive load, then what happens? V2 will be greater than E2. That's why what happens? I'm going to get what? Negative regulation capacity load. Again, coming to this lagging load, you can see where V2 is greater than V2. So what happens? You're going to get the regulation as positive. If I plot terminal voltage as well as a load current, then what happens? I'm going to get graph like this. For lagging, the graph will be like this. For leading, the graph will be like this. And for ideal, it will be straight line, constant line. No any changing with respect to the load current. Irrespective of the load current, you can see the terminal voltage will always remain same. Okay, constant. So the key point what you can see here is the voltage drop should be small as possible, hence less the regulation, better is the performance of the transformer. That's why I'm saying you that best regulation one transformer can have is 0%, not 100%. Okay. And now coming to expression for voltage regulation. In here we discussed here the general expression for voltage regulation. Okay, E2 minus V2 by V2. When you have terminal induced EMF E2 and terminal voltage V2, you can easily calculate the voltage regulation, no issues. Okay, but when the problem has not having values of E2 something or V2 or something, you have to go for the elaborated form of your voltage regulation formula. Like see, you can see the formula here. I don't have any E2, I don't have any V2. Instead of I have secondary current as well as resistance when referred to the secondary, as well as reactance when referred to the secondary. Okay, and V2 in here we have terminal voltage. We have again that other than that E2 is not there. Okay, precise E2 I don't have, but remaining things I have. So I need to go with this formula. Okay. Similarly, for leading power factor, we have formula like this with respect to the primary when referred to primary. We have this formula. Okay, and in generalized formula it has been shown here. Now this is what we are going to discuss. We are going to use this expression for voltage regulation when we don't have E2 directly. Instead of that, we have other things. We need to calculate that first. Okay. And remember, voltage regulation, that is percentage R is nothing but what your voltage regulation, it is always mentioned in what? Either percent or PU. Okay, if you multiply 100 means it will come out in percent. If you don't multiply by 100 means it will be in terms of per unit. Okay. Now remember, expression for voltage regulation is available for both primary as well as secondary. Okay, we have different formulas. Remember that we have voltage regulation formula for both primary as well as secondary. Okay, now coming to this first case is what? Let us say we have connected a inductive load, that is lagging power factor. Okay, this is the first case. We are going to derive the equation for this, that is expression for voltage regulation. Okay, and we know that E2, and since I am taking here E2 as consideration, means we are going to calculate the voltage regulation with respect to the secondary side. Okay, because E2 will come in the secondary, yes or not? So whatever regulation I have written here, it is with respect to the secondary side. Okay, and you can see this is also with respect to the secondary side also. This is the formula, that is E2 minus V2, leading as well as lagging